Welcome to part 8 of a series of videos on multivariable calculus using Mathematica. We are continuing to think about parametric curves. Our main focus in this particular video is on finding and analyzing the speed of an object whose motion is described by a system of parametric equations that will generate a parametric curve. Before I get into that, however, I want to look at the example from the last video once more and emphasize something about it. In that video, we were considering this example where we had a cubic curve, y squared equals x cubed plus x squared. We had a point on that curve, and we wanted to find the slope of the tangent line to the curve at that point in two different ways. First, by using implicit differentiation. Secondly, by using a parameterization that we happen to guess, and that does work. And here is what we got. The slope of the curve at that particular point ended up being -5 over 2 root 2, or if you prefer, -5 root 2 over 4. We found that slope in two ways. One, with implicit differentiation right there. Secondly, with the parameterization using this particular equation right there. Here was the graph that we got. The blue curve is the cubic curve. The dot is the point in question, 1 comma -√3. The black line through that dot is the tangent line to the curve at that point, whose slope is the slope we found. And if I play this animation, I do see the parametric curve coming up in red. It's tracing out the entire given cubic curve. What I want to point out in this video very quickly is that you can also use these two equations, this one and this one, to figure out where the tangent line is horizontal or vertical, though you do have to be careful. And in fact, it turns out in general the parametric equation one is better, at least in this example. For example, we can see that the denominator of this equation is 0 when t is 0, and the numerator is not 0 there. And what that ends up meaning is the tangent line will be vertical when t is 0. This dot that you see right there is the location of the vertical tangent line. Can we find that same location with this equation? Yes, though you have to be careful in thinking about it. That occurs where y is 0. There's two places where y is 0 in this graph though. Right here and right here. Y is 0 because you're on the x-axis at those 2 points. However, if you think about the numerator, you're going to realize you only get a vertical tangent at the place where the numerator is non-zero. At the origin, you really have two tangent lines because the curve passes through that point twice. When you plug in x equals 0, y equals 0 into this dy dx, both the numerator and denominator are 0, and that's sort of indicating that there could be a crossing there, and indeed there is. The tangent line is not vertical there, there's two tangent lines. You can find the slopes of those two tangent lines through the origin with this equation. However, by plugging in t equals plus or minus 1 into this, you will get the corresponding slopes. The slope that goes like this when t is -1, and the slope that goes like this when t is +1. Alright, on to our new example. You can see this is kind of a long example. I'm going to take advantage of Mathematica's calculational abilities to go through this quickly. I would encourage you to try this by hand. We've got a parameterization of a certain kind of motion, and in fact this is the exact same kind of motion as before. I could even copy and paste this stuff down here to see that motion. And what we want to do is we want to find the speed as a function of time. We want to figure out the speed also at time equals 1 second. Graph both the parametric curve showing the motion of the object as well as the speed side by side. Find the value of t where the speed is minimized and find the minimum speed. That's a lot to do. I'm going to see if I can do it here in about 7 minutes or so. First of all, the speed, I'm just going to tell you how to find it here. If I can type. As a function of time, can be found by taking the square root of the sum of the squares of the derivatives of x with respect to time and y with respect to time. I'm just telling you that, just like I told you how to use the other formula for the slope in the last video without explanation. If you know a little bit about velocity vectors, you should know that this is reasonable. What does it turn out to equal in this particular case? I've already entered these functions. I'll get Mathematica to calculate their derivatives, square them, and then take a square root and simplify. You should try this by hand. When you do, we'll see what we get here. You should get this expression. Looks like I've typed everything right. This is the correct parameterization. I'm just trusting that here now. So the answer for the speed as a function of time, written in a standard way you would do, would be square root of 9t to the fourth minus 2t squared plus 1. You should try that by hand. Take those derivatives, square them, add them, take the square root. That's the speed as a function of time. That is the answer to part A. We found the speed as a function of time. How about part B, when time is 1 second? Well, that's easy. Plug in t equals 1. You can do it in your head here. The speed at time 1, you might call that speed of 1, will be square root of, plug in t equals 1, you'll get 9 minus 2 plus 1 is 8. Square root of 8, or if you prefer 2 root 2, that is the speed at that moment in time. In whatever units you're using, it's about 2.8. What are the units that I'm using? We should use those units. Meters per second. All right. Part C, I want to graph both the parametric curve showing the motion of the object as well as the speed as a function of time side by side. How do I do that? I'm going to use all this that I've got here. I'm going to introduce a new command. I probably should have said this command at the start, what it was. It's a command called grid. Take a look at what I have here. I have a show, and inside the show I have a bunch of plotting commands. I'm going to put this in what I think of as the left side of a grid using a command called grid. I will type the word grid here in front of the show, put its end square bracket at the end of the show, its square bracket, its ending square bracket right here. Also, you need to use curvy braces here. I'm going to put 2 curvy braces there, and then between these 2 square brackets I'm going to put a comma and 2 ends curvy braces right there. I could enter this as is right now, and if I did, I would see this picture, a smaller version of what you saw before. Why do I have that smaller version? Well, let me first make it bigger actually. I'm going to add another option in here. Image size, arrow medium. Makes that bigger now. The reason I've got it this way is I'm going to add another plotting command over here. In fact, I'm going to plot the speed as a function of time. Let me go ahead and enter the speed as a function of time first. I can just copy and paste this formula. It's now entered. I want to graph that function over here with the regular plot command. T is going to go from -4 to B. B is the animation parameter. Let's make it, say, thick red. Let's make the plot range go from -4 to 4 in the horizontal direction, and how high in the vertical direction, I'm not sure what the maximum speed is. Let's go up to 50 just to play it safe here. And let's see. I think this is what I want. Oh yeah, I want to also do the image size medium thing to make it bigger. Though I am going to need to make my zoom smaller here, I think. I'm going to go down to 125%. Enter this. Here we go. On the right there, there's the speed as a function of time. Kind of looks like a parabola. I don't think it is. It's definitely not. In fact, let me go down lower to say even 10 here to see it more closely as it approaches the horizontal axis there. By the way, we should probably label the horizontal axis there with the letter T. I could do an axes label. Oops. Copy and paste that over here. And instead of an X, use a T. Instead of Y, use a speed. I should label those axes. Now we see what's going on. It's labeled nicely. There's the speed as a function of time. The object is indeed going more slowly as it rounds the loop here than it is at the extremes because the speed is lower. We've done part C. How about part D and E? What At what value, or values I should say, it looks like, of time is the speed minimized? What we can do is we can take the derivative of the speed, because we want to minimize the speed function. There's its derivative, and we can set that equal to 0 and solve for t. You can see t equals 0 is definitely one root. Solve will be a way we can find the other roots, or you can try this by hand. The other roots are at plus or minus 1/3. Those look to be minimums. You can see they're a little lower than the speed at t equals 0. The speed at time plus or minus 1/3 should be the same. It's an even function. Looks like it's 2 root 2 over 3. Percent sign refers to the preceding output. I can now do percent / capital N to approximate that at about time 0.942809 plus or minus. That's where the speed is. The speed is minimized at plus or minus 1/3, and the minimum speed value is about 0.94 meters per second. Have we answered all the questions? Yes, we have. You might want to rewatch it to write those down and check your work if you try doing this on your own. Here's your exercise. Similar problem. Find and simplify the speed based on some parametric equations. This time distance is measured in centimeters and time is in minutes. We're talking about a bug. Find the speed at time equals 2 minutes. Graph things side by side. Minimize the speed. Here's the speed as a function of time. Simplify as much as possible. I did some things by hand, so to speak. Speed at time 2 is about this, centimeters per minute. And here are the graphs. This one's a little bit more interesting, actually. The speed is not an even function. And you can see it looks like it's minimized near 1. It's actually not exactly 1. If you find the derivative, set equal to 0, use either find root or n solve. Those work more nicely in terms of approximating. The speed is actually minimized at about 0.99 minutes, and the min speed is about 0.99 centimeters per minute. And it's just a coincidence that those happen to be so close together.